Welcome back to Module 2 of the BCT training course on the fundamentals of FWD testing and back calculation of the principles and application of the BCT, which is back calculation tool for rehabilitation design using the PMED software course. Referring back to the BCT training course roadmap, you just finished Session 1 in Module 2. This portion is Session 2 of Module 2 and is on the structure simulation and thickness determination in support of using the BCT software. The learning outcomes for this session are being able to list the rules of the structure simulation for back calculation, create a structure to be used in the back calculation process, understand the importance and impact of layer thickness in back calculating elastic layer moduli, list the procedures for layer thickness determination, and finally, discuss the boundary conditions or limitations for layer thickness determination. 3 topics are covered in this session, which are, first, the rules of layer simulation, second, sensitivity of back-calculated elastic layer moduli on layer thickness, and third, layer thickness determination using standard coring and boring operations and GPR data. Here is another reference material of this course. A Federal Highway Administration report documenting procedures and software for back calculating the elastic modulus of structural layers for all sections within the LTPP program. It was published in October 2022 by Harold Von Quintus and Amy Simpson. 2 other publications are listed on this slide. The one on the left is an FHWA report, which is Back Calculation of Layer Parameters for LTPP Test Sections, Volume 1, Slab on Elastic Solid and Slab on Dense Liquid Foundation, Analysis of Rigid Pavements. The one on the right side is also a publication from FHWA, and this is also from the LTPP program, titled Long-Term Pavement Performance Program Determination of In-Place Elastic Layer Modulus Back Calculation, Methodology and Procedures. 4 additional references are listed on this slide that provide information and background on the back calculation of elastic layer moduli. We're not going to get into the details from these references, but only to say that information was used from all these references to prepare the rules of simulation that are discussed in the upcoming slides. There are 8 basic rules of simulation. The first one is not really a rule, but a limitation of the BCT. A maximum of 5 layers is allowed. The second is to use as few layers as possible because the BCT only allows a maximum of 5 layers. The third is the thickness of the bottom layer should be greater than the thickness of the layer above it. Fourth is combining layers of like material. Like layers will be defined in a following slide, but means the adjacent layers that have the same physical description. Fifth is combining thin layers with adjacent layers of similar materials. Thin layers will be defined and discussed in a following slide. Sixth is to use 2 subgrade layers, upper or weathered subgrade layer and a lower subgrade layer. Seventh, separate subgrade strata at location of groundwater. And finally, include a bedrock or hard layer if present. Now let's overview what defines a thin layer. If we have permanent structure with the layer thickness as shown, none of these would probably be considered a thin layer. However, if a 6-inch lime-treated soil layer is constructed, the 6-inch lime-treated layer could be a thin layer. The 6-inch lime-treated layer certainly does not increase in thickness because its thickness is less than the layer above it. The first arrow, in yellow, illustrates the depth of the lime-treated soil. If a sensor is not located at the surface, which is the depth of the layer, then it is likely defined as a thin layer. In other words, a thin layer is defined for which the modulus of that layer has little to a null impact on the surface deflection basin, or the deflection basin will not capture the response. In order for a sensor to capture the response, that sensor is usually located at a distance from the loading plate that is similar or less between the difference of top and bottom of the layer. When a thin layer exists, there are 2 options for simulating the layer as part of the back calculation process. One option is to fix or assume the elastic modulus of that layer and not back calculate it. The other option is to combine it with an adjacent layer of like material. The 6th rule is to use 2 subgrade layers, a weathered or upper subgrade strata layer and a lower subgrade strata. The thickness of the weathered subgrade soil strata that has been used in the previous studies is between 24 to 36 inches. 24 inches was used for many of the LTPP sites. However, this thickness can be defined by the site conditions. In other words, the depth of the groundwater table or the depth of groundwater or a perched water table. The eighth rule is to use a bedrock or hard layer. Bedrock and other rock formations are normally easily identified through the use of roadway borings and/or other information sources like Soil Conservation Service Series maps. The modulus of these hard layers is typically greater than 300,000 psi. The definition for the use of a hard layer is refusal, or the layer is not contributing any response to the deflection basin. These layers can consist or be defined as a hardpan layer, weathered rock, shale strata, or dry desiccated clay strata. If a hard layer is located around 20 or more feet below the surface, it can usually be omitted or not included in the simulation. A picture of different layers identified through a trench is shown on the slide. The numbers show the different layers. So the question is, how should this structure be simulated for back calculation using the rules of simulation? Using the rules of simulation, combining 3 or 4 of a like material would be a possibility. However, what if the asphalt layers shown from the trench were found to exhibit the condition shown in the slide? How should we simulate that structure for back calculation? Obviously, 8 layers are too many. A possibility would be combining layers 1 and 2 for layer 1, layers 3 and 4 for layer 2, fix layer 5 as layer 3 because it might be a thin layer, combine layer 6 and 7 as layer 4, and assign layer 8 as layer 5. This slide tabulates the individual layers and their thickness listed for an LTPP project. A total of 9 layers were identified. So how should those be simulated for back calculation using the 8 rules of simulation shown on the right side of the slide? Option 1 is one example. For this option, we are combining layers 2 and 3 as like material layers, and combining layers 5 and 6 as like layers, and combining layers 7, 8, and 9 as like layers for a 5-layer structure simulation. But are layers 5 and 6 really like layers? One is a cement aggregate mix, and the other is a JPCP, which probably has significantly different moduli. So option 2 is another example. For option 2, we are combining layers 2, 3, and 4 because they all are coarse-grained materials. We are keeping layer 5 by itself, but fixing the modulus and not back calculating the modulus because it would be considered a thin layer. Layer 6 is an individual layer. We are combining layers 7, 8, and 9 for option 1. So which option is the best for back calculation? The question cannot be answered without knowing more on the actual layers and/or actually doing the back calculation to see what option provides the lowest root mean square error or best simulate the measured deflection basins. This slide summarizes the layer structure and layer thickness for other LTPP sites along with the 8 rules of simulation. There are 8 individual layers for this example. The core shown consists of 2 different asphalt layers, but they are all intact, so the modulus of each asphalt layer could be similar. Option 1 shows a tabular listing of the layer simulation when all of the asphalt layers are intact because they are considered like materials. The structure simulation is the high plastic clay is a layer of layer-separate strata. The sandy clay with gravel is another layer, which is the upper subgrade strata. The lime-treated soil is a third layer, but it is a thin layer, so it is fixed for the back calculation process. The crushed limestone is layer 4, and the existing asphalt layer, the chip seal, the asphalt overlay, and the upper chip seal are combined into one like layer. The other core shown now consists of the upper asphalt overlay and chip seal, which are all intact, but the lower asphalt layer basically fell apart during the coring process. Option 2 shows a different structure simulation if that condition exists for this site. The high plasticity clay is still considered a separate layer as the lower subgrade soil strata. The sandy clay with gravel and lime-treated soil are now combined into one layer, or the upper subgrade soil strata. The crushed limestone is a separate layer. The existing asphalt layer and chip seal are now combined by themselves as a separate layer, and the asphalt overlay and new chip seal are now combined into one separate layer. In summary, Some comments regarding the rules of layer simulation that are listed on the right side of the slide are: no hard rules for layer simulation for back calculation need to be based on reality and condition of layers at time of FWD deflection basin testing. Layers will have to be combined, so lab-derived modulus results will not always match with back-calculated elastic modulus. Engineering judgment will be required. The more you know about the structure and foundation, the better the results. The first three rules of simulation should always apply to all structures. The other rules of simulation may or may not apply and depend on the site conditions and existing pavement structure. The final layer structure used for back calculation should be determined by minimizing the root mean squared error. Now let's move on. How important are layer thicknesses in back calculating elastic layer moduli? Since both layer thicknesses and layer moduli impact falling weight deflectometer deflections, using layer thicknesses for back calculation that are different from the true value in the field beneath the falling weight deflectometer load plate will impact the back calculation results. The two graphs shown on the slide represent the result of changing the layer thickness of a specific layer and determining what impact that thickness change has on the back calculated elastic layer moduli of each layer included in the structure simulation. The graph on the left side of the slide shows the impact of changing the thickness of the asphalt layer by 1 inch below and above the average value measured for this site. As shown in the graph, there is an impact on the asphalt layer elastic moduli. As the asphalt layer increases, there is a decrease in the elastic moduli of the asphalt layer. There is also a small reduction in the elastic layer moduli of the aggregate base layer, with an increase in the asphalt layer thickness, but the decrease or change is within the error of the resilient modulus test. There is almost no change in the elastic layer moduli of the subgrade layer. The graph on the right side of the slide shows the impact of changing the thickness of the aggregate base. As shown, there is a decrease in the elastic modulus of aggregate base with an increase in thickness of the aggregate base, but the thickness change of the aggregate base has almost no impact on the elastic layer moduli of the asphalt layer and no significant impact on the subgrade layer. Let's consider a different example of the thickness impact on elastic layer moduli. The structure used for this example is an asphalt overlay of a fractured PCC slab. As for the previous example, the two graphs shown on this slide represent the result of changing the layer thickness of a specific layer and determining what impact that thickness change has on the back calculated elastic layer moduli of each layer included in the structure simulation. The graph on the left side of the slide shows the impact of changing the thickness of the asphalt layer by 1 inch below and above the average value measured for this site. As shown in the graph, there is almost no impact on the asphalt layer elastic moduli as the asphalt layer increases for this example because the elastic layer moduli is much higher for the layer below the asphalt layer. There is no significant impact on the subgrade layer either. The graph on the right side of the slide shows the impact of changing the thickness of the fractured PCC slab. As shown, there is a decrease in the elastic modulus of the fractured PCC slab layer with an increase in the thickness of the fractured slab. The thickness change of the fractured PCC slab has almost no impact on the elastic layer moduli of the asphalt layer and has no significant impact on the subgrade layer. From the two brief examples, this slide summarizes our general observations or conclusions regarding the impact of layer thickness on the back calculated elastic layer moduli. First, for the unbound layers, the impact of layer thickness on the back calculated elastic layer moduli of the unbound layers is generally within the testing error of the resilient modulus test. The second observation is the layer thickness of the upper and stiffer layer has a greater impact on the back calculated elastic layer moduli of the upper layers and a low to nil impact on the lower layers. And finally, higher accuracy of layer thickness is suggested and beneficial for the bound layer closer to the surface. Overall, layer thickness has an impact, but not a huge impact on the elastic layer moduli. The user or designer should be as accurate as possible for the thickness of all layers, but certainly the upper bound layers. There are two primary methods used to determine the thickness of each layer. Cores and boring, shown in the picture on the lower left of the slide, are the most common method. But ground-penetrating radar, shown in the lower center picture, is becoming more popular because traffic control and destructive sampling of the pavement is not required for this process. The use of GPR, however, still requires some or a few cores and borings or independent knowledge about the pavement structure. Cores and borings are the best and most reliable method to confirm the type of materials and layer thicknesses. A third method can be used along with the coring process, which is a dynamic cone penetrometer, or DCP test. The DCP is used by multiple agencies to determine the stiffness change in unbound layers, including the subgrade beneath the bound layers. Other advantages or added information when using cores and boring for rehabilitation design are identified on this slide. Cores and borings can be used to visually examine the recovered materials from each layer. For example, to determine whether there are material anomalies and confirming the direction of crack propagation or when the cracks are initiated. Determine the condition of bonds between the bound layers, and recover materials for laboratory testing. Another advantage, not listed on this slide, is to confirm the layer thicknesses and material or layer types from GPR tests. Regarding the GPR testing to estimate layer thickness, this slide summarizes some of the advantages of GPR. There are two types of GPR devices or testing. One is an air-coupled device, and the other is a ground-coupled device. GPR estimates layer thicknesses continuously along the project or at close distance intervals along the project for less cost and does not always require traffic control. Use of the air-coupled device generally does not require traffic control, while the use of ground-coupled device typically does. GPR can identify areas with anomalies. Anomalies include severe stripping or moisture damage in asphalt layers, saturated area, etc. GPR can also locate voids beneath the PCC slab. And finally, the thickness data can be collected very rapidly using both the air and ground-coupled devices. However, data processing and interpretation does take some time. In addition, a few cores and borings are usually required from a confirmation or calibration of the layer thickness standpoint. Here's a short video clip showing the ground-coupled GPR device for estimating layer thicknesses. This slide shows a schematic or example of the GPR data. The different layers are identified on the right side of the slide. It is important to note and realize that the BCT does not interpret the GPR data to estimate layer thickness. Deriving layer thickness from the GPR data needs to be completed external from the BCT. Two additional examples will be discussed on this slide. The picture on the upper portion of the slide shows the GPR data for a simple, flexible pavement. The AC layers are designated on the slide, which are supported by an aggregate base. The GPR results show the aggregate base is relatively uniform. The picture on the lower portion of the slide is another but more complex example, which consists of asphalt overlay of a CRCP. The GPR data shows the depth of the steel. Another use of GPR data is to determine the variability and whether that variability changes along the project. This ends Module 2 of Session 2. The next module of the training course is Session 3 of Module 2, which is on the back calculation process and procedure. Thank you.